Hello geographers, just thought I'd take the opportunity today to film a little bit of a run through of something that you all fed back that you found maybe a little bit challenging in your remote learning, which was factors driving plate movement. So what I'll do is I'll go through the main one, which is convection currents. You're likely to have been aware of that at GCSE, but it's always useful to revisit these things at an A-level level. And then I'm also going to talk about the other ones, which are gravitational sliding and slab pull, because they're very new to you and they're very important in the process of plate movement. So I'll start with convection currents and then we'll have a look at those other ones. Okay, so the first thing to remember when we look at convection currents is their own driving factor. So the first thing to remember from your previous lessons is that there is an incredible amount of heat down at the core. So that core is currently running at about 5,000 degrees Celsius for two reasons. The first reason is something called primordial heat. So that's the heat that is left over from our Earth formation, and obviously that is decreasing, but very slowly over geological time, so still pumping out a considerable amount of heat. Then we've got radiogenic heat, so that's the radioactive decay of three isotopes mainly that are down in the core, so that's uranium, thorium and potassium. So as they decay, they're going to be giving out lots of heat energy as a product of that process. So because we've got lots of heat at the bottom of this diagram, or the centre of our Earth, then that heat is going to want to distribute itself with its neighbouring components. So here it's going to be the mantle as we know it. So components of the mantle, or features of the mantle, you will remember are that it is mostly liquid-like. I'll talk about why I said mostly in a second, because we have obviously simplified that down at GCSE and you need to understand it's not quite as easy as that now, but it is essentially a liquid. It can move around and essentially share that energy from the core across the entire span of the mantle, which remember is half of the planet's mass, so it's a big region. So down at the bottom, obviously this mantle here is going to be very hot because it's right next to the core. So we know that when liquids or gases get hot, they become less dense. So they essentially kind of spread out a bit, don't they? They gain size. So because this area becomes less dense and I suppose simply lighter, there'll be areas above it here that are colder, that are less dense, and they're going to be essentially heavier. So what you're going to get is because remember this is mostly liquid like, is you're going to get a movement upwards from the core. So initially you're going to get that rock starting to rise. It's less dense than all the stuff up here, so it's going to be lighter and rise to the top. So if I just put two of those in for now, and I'll explain why I'm doing that in a second. So obviously as it's moving away from the core, this rock, this mantle that is less dense and lighter, is going to start to cool a little bit, and that's going to make it heavier. So it will reach into the asthenosphere. So the asthenosphere is the bit, as geographers studying hazards, we're most interested in. It's the semi-molten part of the mantle at the top. So like I said earlier, not completely liquid. The further up towards the lithosphere, the crust that it does get, it does start to become semi-molten. So it will get up to that section, and it is probably moving quite slowly now because it's not as liquid-like, but it's definitely cooler. So what will happen is that actually it will kind of brush against the lithosphere at the top, but it will, like I said, get heavier, more dense because it's cooler, and then it will start to sink back down again. So that's going to happen all over the mantle, and basically end up kind of back where it started once that process has begun, because remember it will have that push of new magma coming up from the core, which will continue to push and drive it downwards. So it becomes a bit of a cyclical process. So the reason I've drawn two here is you'll notice that I've drawn a constructive plate margin here. So we have got, it could be oceanic, and I think as I've drawn this in my head, that's what I've created, because I've done a little bit of a mid-oceanic ridge here. So what will happen is that as these convection currents diverge, they move away, then that's actually going to cause movement of the lithosphere, the plates on the top, and they will be dragged due to friction in those two directions. Now obviously the convection currents could be doing something slightly different, so I'm just going to pause the video, draw a destructive plate boundary and show you how that convection movement can lead to a slightly different or a very different process on the surface. Okay, so just so that you don't have that constructive plate boundary stuck in your mind as the only way that these things work, it's really important with your plate boundaries that you understand what the convection currents are doing in each of them. So with these sorts of plate boundaries, which are destructive, and again, just because this is probably the one you're most familiar with, I've drawn one that's oceanic on this side and continental on this side, leading to that subduction. It could be that you have convection currents moving in a slightly different way. So if you kind of had the rising of heat occurring here, you get that whole kind of cooling, friction, dragging, sinking, dense magma, and then that return of that process. And then you can also have perhaps the kind of heat kind of rising in this area and then moving around and then dragging that continental plate. So you can see in my other diagram that it was quite different. Those plates were actually, the convection currents were diverging, they were moving away from each other, but here we've got them moving towards each other. So just remember that obviously with these convection currents, it depends what they're doing as to what those plates are also going to be doing and how that lithosphere is reacting on the surface. So that's convection currents, and I think most of you might remember those from GCSE, but like I said, at an A level, you just need to make sure that you can talk about what they're doing in the context of each of your plate boundaries. Okay, so as we finished convection currents on destructive plate boundaries, I thought we'd now start with slab pull. So I've drawn a very similar diagram here. I suppose it's slightly more close up because I haven't included the core, but we've obviously got our oceanic plate here. So remember that the oceanic plate is going to be the heavier one. It's made up of things like basalt, silicon, magnesium and oxygen, so and it is also younger, but it is much denser, mostly due to the basalt. And then on this side we have got the continental plate. So these plates are going to be lighter, they are formed more so of things like granite. They're also generally a lot thicker, which is perhaps not as clear on my diagram. I probably should have drawn it slightly more like that. And they do also float on the asthenosphere a bit more because of their lightness. They're almost kind of bobbing along as iceberg type kind of formations, if you imagine an iceberg on the ocean. So they don't descend or subduct as oceanic because of that. They are floating almost above the asthenosphere, whereas the oceanic plate is almost compressing the asthenosphere down a little bit. So with this one, the slab pull element is an additional force occurring at any plate boundary where there is subduction. So the most important bit that you need to realise in this area is that obviously you have got that subducting region. So we know this plate is particularly heavy, and we know that it is actually going to be colder than all of the other kind of components around it. So as it starts to subduct down, it's much colder than the mantle or the asthenosphere, and it's also very heavy. So if you put your knowledge of what happens in a convection current into this, you'll know that if something is cold and it's surrounded by an area that is warmer and it's liquid and it has that ability to do it, it is going to sink. So you're going to find that even just the fact that it's colder and very dense is going to almost promote that extra gravitational pull downwards towards the core. Obviously it will never get to the core, it's going to melt far kind of earlier than that would ever happen, but it is going to drop down due to that extra gravitational pull because it's very cold and it's very heavy. A way to kind of imagine this, and my students might have heard me use this as an example of how it would almost exist in your world, is if you or maybe somebody you know has something heavy attached to your school lanyard, and you try and put it in your pocket, but the heavy section of it, so the bit near the badge, starts to fall out, but that kind of tether bit, the kind of string bit, is still in your pocket. Think about what that's going to do. The heavy, dense part of that item, being, I don't know what it is, the keys or the badge itself, is going to tug and pull at the rest of that item, the kind of string, almost necklace section. So that's going to pull that down and out of your pocket, and it's the same sort of thing occurring here. So one thing just worth noting here is actually that we think that this has a far greater impact than we ever thought maybe 20-30 years ago. We think actually at destructive plate boundaries, where we've got that huge pull on that oceanic plate, that slab pull is actually perhaps playing a greater part in this process than we originally thought, and perhaps even more so than the pull of the convection currents. So obviously it's one of the reasons why we also end up getting lots and lots of earthquakes occurring on this Benioff zone, this kind of subduction area, because that's where we've got that additional force occurring. So that's your slab pull, and you only need to talk about that in the context of any subducting destructive plate boundaries. Okay, so the final one I'm going to talk to you about today is the factor driving these plates moving around, called gravitational sliding. So this one also has another name. It's often termed ridge push, but a lot of experts actually do prefer gravitational sliding because it's probably more descriptive of the process that is actually going on. It's also different, or very different, to slab pull, so it's probably going to be easier for you to remember that as well. So for the process, for the reasons I've just set out, let's refer to it as gravitational sliding. So this is going to occur at a constructive plate boundary. So those convection currents are going to be diverging, they're going to be moving away from each other, which is going to be causing these plates to move apart as those convection currents are dragging either way. We're going to use the example of oceanic and oceanic here because, again, it's the one that is used the most in the textbooks, and I think that probably means we've got the most evidence of it occurring at oceanic constructive plate boundaries. So the thing to note here is this section of upwelling. So this convection is, quite forceful. It's moving from the core up to the area of the asthenosphere and hitting the crust, or as we should be calling it, the lithosphere. So what that's going to do is it's actually going to push the plates upwards. The force of that upwelling is going to force it upwards. So if I just adapt my diagram to kind of show that, and this is quite important, understanding this in the context of rift valleys, so I might talk about that in a different video, but for now let's just keep it simple with regards to the theory. So what that's going to do is it's actually going to push the plates up a little bit. So we think that that is probably going to be the effect of about 2 to 3 kilometers. So in the grand scheme of things globally, obviously this is probably quite exaggerated here, but it is going to play a bit of an impact in the next stage. So that plate is pushed upwards because of this big upwelling, bringing new hot magma to the surface. So what you need to realise now is that we've got an area here which is higher up than the rest of the plates, and it's moving away from each other either side. So gravity is going to be playing quite a considerable part here. It's only a couple of kilometres, but it is a large heavy plate. So because it's slightly higher, it's kind of going to pull itself, due to gravity, it's going to pull itself downhill. And of course downhill is away from the plate boundary. So you've got this normal process of moving apart, but on top of that you've got this section of the plate almost kind of pulling itself downhill due to gravity. So you've got that additional push in the same direction. So you'll probably know from your studies of physics at GCSE that if you add two forces of the same direction together, then that is obviously going to increase the speed at which these two plates are moving together. So I notice I've put a lot of arrows here now, and it's potentially looking like quite a confusing diagram, but what I want you to realise is it's an additional force. Because these convection currents are pushing this part of the plates upwards, it's creating a gravitational force on this section which is pulling it downhill and away from that plate boundary. So like I said, it's really important we understand that for Rift Valley formation, but I will discuss that in another video. So I hope that has helped you. It's really important to remember here that all of these processes will be acting in different contexts. So there will be some plate boundaries where convection is having the greatest impact. There will be other areas where gravitational sliding or slab pull is almost taking the lead a little bit. Our world is a very complex place, and it does very much depend on lots of different things, like the exact direction of the plate movement, the type of plate itself and all of its components. But as long as you're aware that they all exist and that you know which ones exist on a destructive plate boundary, so don't forget that will be slab pull, and on a constructive plate boundary like this one, it's going to be convection aided by gravitational sliding at that plate boundary itself. So again, hope that helps, and if it still doesn't make sense, then do make sure that you mention that to your teacher the next time you see them, either remotely or in person in school. But yes, hopefully this will help you just start to really piece together those factors driving those plate margins in all sorts of directions.